Hello everyone and thanks for joining my talk today. Mesh subdivision lets us represent smooth freeform surfaces as coarse control meshes which are evaluated using iterative refinement, where new vertices are added to the mesh and existing ones are updated. Subdivision surfaces were already introduced in the 70s through the concerted effort of several pioneering researchers. In 1997 they were first used by Pixar in an animation movie called Garry's Game, which sparked a rapid increase in popularity of subdivision surfaces. Nowadays, they've become a cornerstone in the movie industry and even found their way into video games, which is why many efforts were made to evaluate subdivision surfaces efficiently in parallel. In general, there are two main categories of parallel subdivision approaches. Patch-based approaches split the mesh into patches which can be subdivided independently. While this can be parallelized efficiently, patches have to overlap, introducing redundant data and redundant computations. Furthermore, cracks between patch boundaries might be introduced due to floating point errors. Table-based approaches are very efficient in re-evaluating vertex data, for example in animated meshes during rendering. But subdivision tables depend on the mesh connectivity and their computation accounts to a full symbolic subdivision, which is expensive. Table-based approaches, such as the current industry standard OpenSubdiv, perform very well in rendering, where mesh connectivity is considered static. But their applicability in other use cases, like modeling and design of subdivision meshes, is limited. Whenever a connectivity changing operation is applied to the mesh, a recomputation of the tables is performed, which introduces unpleasant idle times for the artist. Therefore, different approaches are used in different stages of the production pipeline. The results of these approaches vary in detail, causing discrepancies in the results. We propose a one-stop shop solution for efficient mesh subdivision that can act as a drop-in replacement for the different approaches. Our approach is motivated by sparse linear algebra formalizations, which are easy to understand and manipulate by all practitioners. Furthermore, the descriptions are platform independent and basic linear algebra systems are available for almost any hardware. We use a sparse matrix as the underlying mesh representation called the mesh matrix. Each face in the mesh corresponds to a column in the matrix, and each vertex is represented by a row. Here in this example, the first column corresponds to the first face, has non-zero entries in the rows of its vertices. The values of these non-zero entries are the traversal order of the vertices when traversing the face in winding order. There are many different subdivision schemes that lead to different results with different properties. Probably the most commonly used is Catmull-Clark subdivision, which can be applied to polygonal meshes and exclusively produces quads independent of the input face type. While we have multiple schemes in the paper, this talk will be focused on Catmull-Clark, which consists of 4 steps. In the first step, a face point is computed for each face as the average of the face's vertices. The second step computes an edge point for each edge as the average of its endpoints and the 2 adjacent face points. The third step updates the vertices of the control mesh using a linear combination of the vertices in the one-ring neighborhood. The last step reconnects the new vertices to build the refined topology. For the face points, we need the number of vertices in each face. We can compute face orders efficiently using the mapped SPMV here. The notation tells us that we map each non-zero value in the mesh matrix to 1 during the multiplication. We are only using the sparsity pattern of the matrix and substitute the data on the fly without generating additional data explicitly. This mapped SPMV effectively counts the number of non-zero values in each column, which is equal to the number of vertices in each face. A mapped multiplication of the transposed mesh matrix with the positions efficiently computes the face points. We substitute each value in a column by the reciprocal of the corresponding face's order to average the face's vertices to a face point. As from the second iteration on, all faces in the mesh are quads, we can omit the computation of face orders and substitute all values by 1/4. To compute an edge point, we need the 2 endpoints and the 2 adjacent face points. We can generate this information using a mapped SPGEM. During this multiplication, we multiply a row of M with a column of its transposed, both corresponding to a vertex. Whenever 2 non-zero entries meet, we call this a collision. Such a collision only happens when the corresponding vertices share a face. What is actually the information we want to extract from this multiplication? We want to know that face L borders the edge ij. In a conventional matrix multiplication, the 2 non-zero values would be multiplied and accumulated. What we do instead, whenever a collision happens, is to call a lambda function with the information about the collision. We know that a collision happened between vertex I and j in face k, and we have the non-zero values that cause the collision, the position of the vertices inside the face. But this is not quite enough, because the result would now be the sum of the two neighboring face indices, because we will get one collision per shared face of I and j. This is where our action maps come into play. These action maps encode relations between vertices inside a face. This action map here encodes counterclockwise connectivity inside a face. It tells us that the first vertex is connected to the second one, the second to the third one, and so on. When we multiply row I with column j, the lambda function will now only return the face index for the collision in face L. Using f, we can simply compute all edge points because it stores the indices of neighboring faces for each edge. What remains is the assignment of indices to each edge. To enumerate mesh edges, one can simply enumerate the upper triangular part of its undirected vertex-vertex adjacency matrix. We can create a matrix that has the same sparsity pattern as the adjacency matrix using a similar action map as before. Now the map encodes both clockwise and counterclockwise edges, and the lambda function simply returns the map value. For each pair of vertices, we get a number of collisions equal to the number of faces they share. The resulting matrix holds the number of shared faces for any pair of vertices. We can assign unique indices to the upper triangular part and thereby to the edges. With this information, the edge points can be computed. In the next step, we have to update the control vertices. The update can be split into 3 terms, each depending on the valency of the vertex. The vertex valency can be computed similar to the face orders using a mapped SPMV. By replacing non-zero entries by 1, we count the number of faces around each vertex. The first term can be computed in customary ways as it is just an element-wise operation. The second term averages the neighboring vertices. We do that using a mapped SPMV of the matrix F with the positions. Each row in F corresponds to a vertex and has non-zero entries in columns corresponding to its neighbors. Each non-zero value in a row is then substituted by the valency-dependent term. The third term computes a weighted average of face points around each vertex. A mapped SPMV of the mesh matrix with the vector of face points computes the average efficiently, as each row in M corresponds to a vertex and has non-zero entries in columns corresponding to neighboring faces. After this third step, all refined vertices have been computed. What remains is the topology refinement. This is similar to the computation of F from before in that we want to create one output per directed edge in the mesh. Now instead of a face index, we want to output one of the faces in the refined mesh. In this small example, let's first look at the edge between vertex I and j. During the multiplication, we will get the collision between these vertices, and the map will confirm that they are connected in counterclockwise order in that face. This means the lambda function will generate an output, namely the refined face that borders the edge. The refined face generated comprises the index of the original vertex, the index of the outgoing edge point, the index of the face point, and the index of the edge point on the incoming edge. This refined face is stored in Tij. As the multiplication progresses, we will get the total of 4 collisions in that quad, each emitting one of its refined faces. At this point, we have a formalization of Catmull-Clark subdivision that is completely platform independent. Now we can take this further and make the step to the GPU. Our approach is implemented in CUDA, so I will use CUDA nomenclature in the following discussion. We slightly modified standard SPMV and SPGem kernels in order to enable the usage of maps and lambda functions. These operations require a large amount of independent computations and therefore comprise a lot of potential parallelism. These modified kernels are great for prototyping and already provide very good performance. Moreover, the implementation is abstracted from the application as the SPLA operations steer the data movement and maps and lambda functions determine the actual result. That also means that applications that implement these formalisms will profit from future performance increases in SPLA kernels. But as we will see in a minute, the formalizations hint to even more efficient implementations. We can use the knowledge about the domain and the underlying data in order to optimize the standard kernels to further increase efficiency. We use the compressed sparse column format to represent sparse matrices in our implementation. The CSC format consists of a total of 3 arrays. The first 2 store 1 entry per non-zero entry in the matrix, namely a row index and the corresponding value. A third array stores the beginning of each column in the other 2 arrays. Column offsets and row indices determine the sparsity pattern of the matrix, and the values store the actual data. In the following, I want to show you 2 small examples and how our formalization steered the specializations of these kernels. The first example is the computation of phase points in a quad mesh. This is the pseudocode of a straightforward implementation that does not consider any knowledge about the underlying data or the domain. What happens here is that each thread works on one column. First, it determines the start of its column in the column pointer array, and then starts to read the row indices one by one. For each of the row indices, it reads the corresponding vector entry and accumulates them. After all entries in the thread's column have been summed up, the value is averaged and the final phase point is written to the thread's output vector element. But we actually know a bit more about the underlying data. First, the fact that each column has exactly 4 entries renders the column pointer obsolete. Therefore, we can assign one thread to each row index. 4 consecutive threads work together to compute a single phase point. They do so by reading their row index and the corresponding vector element. The vector data is then summed up in a parallel reduction using fast warp-level communication primitives. Then the final phase point can again be computed by averaging the accumulated value. The second example is the mapped SPGem that performs the mesh connectivity refinement. A sparse matrix-matrix multiplication usually involves multiplication of each row of the left matrix with every column of the right matrix. As we are multiplying a mesh matrix with its transpose, we can avoid a large number of computations. We know that we will not get a non-zero entry in the result if the 2 vertices do not share a phase, because no collision will ever happen. When we now only multiply vectors that actually cause a collision, there will still be invocations of the lambda function that return 0, because the map does not confirm the encoded relationship between the vertices. This means we know exactly which pairs of vertices will generate a non-zero result. Those vertices that are connected by an edge in counterclockwise order in any phase. This speeds up the computation drastically. In the bottom right, we see the pseudocode of the optimized mapped SPGem. Similar to the previous example, we can now parallelize over the non-zero entries of the mesh matrix. Each thread handles a single collision and produces one refined mesh phase. First, each thread reads the vertex index of the original vertex it is assigned to. To determine the edge point on the outgoing edge, each thread needs to know the next vertex in the phase. As this index is already known by the thread assigned to it, we can use efficient warp-level communications to determine it. With v0 and vn, the thread now uses e to determine the index of the first edge point. The index of the phase point can be computed from the thread's position in the row indices, as each phase has exactly 4 entries. The last index of the new phase is the index of the edge point on the incoming edge. This index was already determined by the predecessor thread in the phase and can therefore be communicated efficiently using warp-level primitives again. Now, each thread holds one refined phase in registers. The result can be written to memory using efficient vectorized stores with perfect write access, as consecutive threads write consecutive refined phases. This already concludes the topology refinement. In the evaluation, we compare 3 approaches. First, our implementation of Catmull-Clark using standard SPMB and SPGem kernels that were only slightly modified to allow for action maps and lambda functions. The second version of our approach uses the specialized kernels that take into account the underlying data and the domain knowledge. The third approach is the current industry standard OpenSubdiv, which operates in 2 steps. They perform pre-processing on the CPU, where they refine the topology and compute their subdivision tables. In the second step, they use the pre-computed subdivision tables on the GPU to refine the vertex data. All our evaluations were performed on an Intel i7-7700 with 32 GB of RAM and a GTX 1080 Ti. Before we discuss the numbers, let's first see Slack and OpenSubdiv in action in a short modeling session. For both approaches, we showed a preview of the subdivision surfaces at level 5. In this demo, we apply simple modeling operations to the control mesh of the big guy model. While Slack shows instantaneous updates of the subdivided results, OpenSubdiv requires trips to the CPU on every connectivity changing modification to recompute the subdivision tables, which introduces these unpleasant delays and clearly breaks the interactive feel of the whole modeling experience. Slack, on the other hand, does not require any preprocessing and is natively parallel, which allows for this smooth, consistent real-time preview. We selected a variety of differently sized meshes and subdivided them to different levels. Please note that the performance chart is in log scale. We split the timings for OpenSubdiv into 2 parts. The gray bar shows the total time for the subdivision including preprocessing, and the green bar is the evaluation of vertex data on the GPU. For lag and Slack, the complete subdivision time is shown. we can see that Lag already achieves a good speedup, on average 26.6x compared to OpenSubdiv, although it is using the standard SPLA kernels. Slag is then on average an order of magnitude faster than Lag, which indicates that our specializations were highly effective. It is interesting to see that the GPU evaluation of OpenSubdiv is in most cases not too much faster than the entire subdivision using Slag. One exception is the Angel model, which is only subdivided to level 1, where Slag cannot unfold its full potential. Concerning the peak memory consumption, Lag needs similar or slightly more memory than OpenSubdiv due to the explicit storage of all of our matrices. Slag reduces the required memory significantly, as some data, for example F, do not need to be created explicitly and thus stay significantly below Lag and OpenSubdiv. We think that the sum of all those results makes Slag a well-suited drop-in replacement in modeling tools to provide highly detailed previews of subdivision surfaces without inducing unpleasant idle times after each connectivity-changing modeling operation. Our formalisms naturally extend to other subdivision schemes, such as loop and square root 3, where we also outperform the competitors. You can find the details in the paper. We've seen that our approach performs very well when we subdivide topology and vertex data in each iteration. But there are applications such as rendering of animated meshes where the connectivity stays the same for many iterations, which is the target use case of OpenSubdiv. In this case, it makes sense to invest more resources in the preprocessing step in order to speed up evaluation of vertex data. As each vertex in the refined mesh is a linear combination of vertices in the control mesh, we can write the vertex data refinement or evaluation as a sparse matrix vector multiplication. In our subdivision matrix, rows correspond to refined vertices and columns to control vertices. We built the matrix using only the adjacency information we also generated in the dynamic mesh case. In the first step, we determine the number of non-zero entries in the matrix to create the empty sparsity pattern, which is then filled with weights in a second step. Most of the time, we want to perform multiple iterations of subdivision instead of just a single one. We can simply multiply the individual subdivision matrices to get a single matrix that performs several iterations in one shot. So now that we have a subdivision matrix, we want to use it to perform the evaluation of vertex data. There are many very efficient SPMV implementations for GPUs available, and it is still a very active field of research. One very important aspect when optimizing GPU SPMV is load balancing between threads, as the execution takes as long as the longest running one. This means that the available amount of work needs to be distributed evenly among the available threads. SPMV implementations usually apply some sort of dynamic load balancing that analyzes the matrix at hand and adapts the load balancer accordingly. This, of course, introduces some overhead for the analysis. The subdivision matrix does not change between consecutive evaluations. Therefore, we can compute the static load balancing in preprocessing, which is reused in the evaluations. We use a very simple load balancer that assigns each thread the same number of non-zero values of the matrix. Each thread then accumulates its data locally and combines it with the partial results of other threads. The final result is then written efficiently to global memory. This strategy keeps the overhead low and the load is effectively balanced among the available threads. The evaluation is split into two parts. On the left, we can see the preprocessing time. For OpenSubdiv, this means refining the topology and computing the subdivision tables on the CPU. Slag computes the adjacency information, refines the topology, and assembles the subdivision matrix on the GPU. The GPU preprocessing of Slag is on average more than one order of magnitude faster than OpenSubdiv's CPU preprocessing. But as we consider the mesh connectivity static in this use case, the by far more interesting result is the evaluation of the vertex data on the right. Here, OpenSubdiv uses the pre-computed weights to refine the vertex data, while Slag performs its SPMV. While both evaluations are quite similar in their nature, Slag outperforms OpenSubdiv by 1.6x on average, which underlines the efficiency of our SPMV evaluation. The peak memory consumption is quite similar for both approaches, as OpenSubdiv's subdivision tables basically encode the same information as our subdivision matrix. These results indicate that Slag can not just be used in cases where the mesh connectivity changes frequently, but also for subdivision of animated meshes during rendering. This almost concludes my talk today. We introduced a framework to perform subdivision based on a sparse linear algebra abstraction. Everything runs completely on the GPU, from topology subdivision to vertex data refinement. Slag can handle different application scenarios. Whether mesh connectivity changes frequently or not at all, Slag provides good performance. Our approach is capable of handling extensions such as semi- and infinitely sharp creases and also selective subdivision, where only certain parts of the mesh are subdivided, for example around extraordinary vertices. While this talk clearly focused on Catmull-Clark subdivision, we also have loop and square root 3 in the paper. Of course, the source code is freely available. Thank you very much for joining me today. The QR code contains my contact and a link to the source code, so if you are interested, please feel free to check it out. I'm looking forward to your questions.